Welcome to video 2.5, moles and atomic conversions. We're going back to the world of conversion problems. And as we get started, two pieces of resources you're going to need is your periodic table that I gave you in class and this thing called the mole map. This mole map is found on page 63 of your workbook. So pause the video, grab your periodic table, and grab your mole map. So in this video, we're going to understand and you're going to be able to explain the concept of the mole, Avogadro's number, and the molar mass. Then we're going to perform some conversion problems between moles to number of atoms / particles or molecules, and then also convert to grams of a given substance. So a couple of key terms you'll hear is the word mole, Avogadro's number, and molar mass. And again, if at any time you're not understanding the definition through use in context, pause the video and Google these numbers to get a better idea. So the mole idea, the mole concept. You already learned that the mole is the SI unit for the amount of substance. And the mole is just an amount. It can be represented as a number, it can be represented as a mass, it can even be represented as a volume. So think of it like the term a dozen. We understand what a dozen donuts are. We understand that a dozen means the number 12. So if I have a dozen donuts, I have 12 donuts. But then depending on the thing we're talking about, that dozen also has a set mass. So in the case of donuts, 1 dozen donuts equals 12 donuts, which also equals 1.48 kilograms of donuts. Now, if I talked about elephants, I could have a dozen elephants. I would still have 12 elephants, but the mass would be very different. So the mole idea is exactly the same idea, except instead of working with the number 12, we're working with this really large number called 6.02 times 10 to the 23 atoms. So the way this number came up was scientists, again, started with the carbon-12 atom. They took the carbon-12 atom, and they found 12 grams of it, and then they counted the number of atoms that were in 12 grams of carbon. When they did that, they found out that 12 grams of carbon has 6.022 times 10 to the 23 atoms in it. Then, when they calculated out copper, they found the same number of atoms there in copper, but then when they took the mass, it came out to 63.5 grams. So now we're starting to get this reference of the mole concept, that a mole is just a number that can also be expressed in a mass, which you'll find off your periodic table, and again, down the road, you'll see how it could be expressed in a volume, depending on which kind, also depending on what we're working with. And so as we move forward, we see that the mole concept is this number, 6.022 times 10 to the 23 atoms. This is called Avogadro's number after Amedeo Avogadro, who created this idea, who discovered it more or less. And we're going to use this as a conversion factor. We're going to use the number, and we're also going to use the mass as conversion factors in our conversion problems. So again, think of it like a dozen. A dozen is 12 donuts, and a dozen has a certain mass. A mole of anything is exactly 6.22 times 10 to the 23 things per that thing. And so since we're talking about atoms, in a mole of carbon, we're going to say 6.22 times 10 to the 23 atoms is 1 mole of carbon. But then also you're going to see that that 1 mole has a mass of 12 grams. Same thing for copper. 6.022 times 10 to the 23 atoms of copper equals 1 mole of copper. And then that 1 mole of copper now is going to equal 63.5 grams, which again, you find these numbers off the periodic table. The masses come off the periodic table. So let me show you where that's at. If you look at your periodic table here, in the bottom left corner, you're going to find what's called the atomic weight, that red number. That red number is going to be the molar mass, or the atomic mass. Depends on how you want to look at it. So we've already learned that as the atomic mass. Now we're going to consider it the molar mass as well. So when we call it the molar mass, we're going to use that number to 2 decimal places, just like we did when we talked about the atomic mass. And we're going to change the unit from the AMU to grams per mole. So what is a molar mass? A molar mass is the amount in grams of 1 mole of an element or compound. Let's say that again. It's just the amount in grams per 1 mole of an element or a compound. So we say 60 miles per hour, that means we went 60 miles in 1 hour. When we say 12 grams per mole, we have 12 grams for every 1 mole. And this, again, will be a conversion factor we're going to use. So notice, though, that the molar mass will increase depending on which element or compound you're dealing with. When I look at carbon, carbon has 12 grams per 1 mole. Hydrogen, an individual hydrogen, only has 1 gram per mole because it's smaller. There's only 1 proton there for every atom. And again, if you look at mercury and iron and sulfur, they all have different masses. And again, where do I come up with these numbers from? Then we use the conversion factors here in a second. We get them off our periodic table. Here you can see hydrogen is at 1. You can see carbon as 12. You can see mercury down here as a 260, I think it says there. Or 200.6. But again, molar mass is just simply the mass of 1 mole, grams per 1 mole. So when I go from talking about individual atom, now we're going to talk about a compound. This compound is lithium chloride. So if I want to find the mass of 1 mole of lithium chloride, all I do is add the individual molar masses of lithium and chlorine. So again, I go back to my periodic table. I see the mass of lithium chloride as lithium being 6.939 grams per mole and chlorine being 35.453 grams per mole. And again, then if you added those numbers up, we're going to get a 42.392 grams per mole. Now, one thing for this class, to keep us all on the same page, we're going to cut these numbers down to 2 decimal places. So when you look at your periodic table and you see where it says 6.941 on our table and this one says 6.939, we're going to go ahead and cut that down to 6.94. We're going to cut this down just to 35.45, and to keep it nice and easy, when we add those numbers, we're going to use what we get there, which would just simply be 40. So again, a small change, but it's going to keep us on the same page if we just go to 2 decimal places all the time when we're dealing with molar mass. So again, 2 decimal places, 2 decimal places, and then when you come to put that number in your calculations down below, just go to 2 decimal places, which you'll see here in a second. All right, so as we move on, now let's look at, we have a compound here. Before we had a compound that just had a 1-to-1 ratio. There's just 1 lithium, 1 chlorine here. So now we're going to do the same thing of a mass that has multiple atoms in that compound. Same idea. We're just going to take the mass of each individual atom here, just like we did here. We take the mass of each individual atom, added it together to get the molar mass of the compound. Same thing here, the mass of all these individual atoms, except here I have 3 calciums and I have 2 nitrogens. So if you want to show your math like this, you can. If you want to write this off to the side, that's fine. But we want to show that we have 3 calciums there. And if you look at your periodic table again, you will see calcium is 40.08 when I cut it down to 2 decimal places. And then we have 2 nitrogens. And if I cut nitrogens down to 2 decimal places, we get 14.01. So add all that together. These get multiplied, these multiplied, add together, get 148.26 grams per mole. Again, there's a couple ways you can do it. But this is the easiest way to show it that you can understand mathematically. One other thing is if you get a compound like this where you have calcium and you have this, I believe it's nitrate within parentheses, you're going to again just use distribution, just like you did in math class. Follow your distribution properties. This 2 here actually tells me I have 6 oxygens and 2 nitrogens here. So again, we're just going to write it all out. Put down the molar mass of calcium. We're going to take the molar mass of nitrogen, multiply it by 2, and then take the molar mass of oxygen, which is 16, multiply that by 6. Again, where did this 6 come from? Because it's 2 times 3. Where did this 2 come from? Because this 2 gets distributed, and there's 2 nitrogens here. So I'll show you how that will look here in a second on paper. But again, make sure you have this mole map out, and I want to show you how to use it in this practice problem number 1. So here's the grunt of it, the problems that we're going to be doing. I'm going to show you 3 practice problems that you're going to be doing in class, and then the next 3 days in class, we're just going to be practicing, because it's not super challenging. It's just a path you got to learn how to do, and a certain way of thinking you got to get under your belt. So practice problem number 1. How many moles of silver are there in 3.01 times 10^23 atoms of silver? So obviously, we want to start with looking at the problem and see, okay, what did they give me in the problem? Well, I was given 3.01 times 10^23 silver atoms. This is what I know. I know this from the problem. This is my starting amount, because again, we're just doing a conversion problem, and so we got to write down what we know. Write down what you know. And then the other helpful thing as you get started here is write down your unknown. Where are you going to? What are you trying to answer? And the question says you want to know moles of silver. Moles of silver. So you might want to write that down as your unknown. And then we're just going to use our mole map to find this correct path. So I'm going to start here. I just want to get you in the habit of using this, because as we get harder and harder problems, this mole map is going to be a very useful tool. So let me show you what this means. So how do I use this? Well, first of all, you have to start on your given. So we know we have 3.01 times 10 to the 3 silver atoms. So that's this box right here. You see where it says particles? This particles idea just represents the idea that it could be in atoms, it could be molecules, it could be formula units, it could be elephants, it could be donuts. This particle idea is just something small. And that conversion here between particle and mole is 6.022 times 10 to the 23 atoms of silver. And we'll talk more about that in class. But the idea here is I want to start here on atoms, and I'm just going to convert it to moles. So I'm going to start with atoms. I'm going to do step one. I'll write down what I know from the problem. I know 3.01 times 10 to the 23 silver atoms. I'm going to follow my units. Atoms of Ag here, I have to write atoms of Ag here. This is why when we did dimensional analysis, it was so important you learn to follow the 3 steps. Write down what you know from the problem, follow your units, atoms of Ag, and now step 3, get a conversion factor. This video is teaching you that 1 mole of anything equals 6.022 times 10 to the 23. 1 mole of anything equals 6.022 times 10 to the 23. That's why this word particle is being used here. It's a very generic term that can be anything. In this case, we're talking about an individual atom of silver. So I wrote down what I knew, I followed my units, and then I got my conversion factor. 1 mole equals 6.22 times 10 to the 23 atoms of silver. Multiply it out. Multiply across top, divide across bottom, you get 0.500 moles of Ag. I started with 3 sig figs. I will end with 3 sig figs. Now let's look at the next problem. Go ahead and you can watch me do it, or if you're getting confident, go ahead and pause the video and try it yourself. But the idea here now is, again, I'll show you with my own hand how I work through and think about this problem. So how many moles are there in 42.3 grams of calcium? So what did the problem give me? It gave me 42.3 grams of calcium. I think I said carbon, I meant calcium. What's the unknown? It wants me to determine the number of moles. So I like to put a question mark here, moles. And I always want to put my units here. We're talking about moles of calcium. So this is where I'm going to start. This is where I'm going to end. If I refer back to my mole map, what does that mean? Well, I have grams. We know grams is a mass. And I want to convert it to mole. So what we can see here is I can convert from here to here, from here to here, using the molar mass. I'm going to write that right here. Molar mass. Now, where do I find the molar mass from? I find it from the periodic table, PT. If you want to write this on your mole map, you can. That will help you out, because eventually you're going to be doing all kinds of conversion problems using this mole map. But this is a good place to start. So if I'm in mass and I'm going to go to moles, I'm going to use what's called the molar mass. That's from my periodic table. So where do I find that number? Well, if I look on my periodic table, I find calcium, and I see this number here is 40.078. I'm going to cut that down to 2 decimal places, and I see that 1 mole of calcium has the mass of 40.08 grams of calcium. Okay? So this is my conversion problem, or my conversion factor. This is what I know. This is where I'm going. And now we just simply do our 3 steps to do a conversion problem. We write down what we know. I know I have 42.3 grams of calcium. I'm going to follow my units. I know from grams I can go to moles. So it automatically tells me the only place I can go from grams is to moles of calcium. And then now I have to make this a true statement. How many moles equals how many grams? Well, I just saw my periodic table. 1 mole equals 40.08 grams. Now I just simply put that in my calculator. I'm going to multiply across the top times 1. And then I will divide across the bottom. And I get this answer of 1.055. I have 3 sig figs here, so I get a 3 sig figs here. So I round it to 1.06 moles of calcium. Now, grams cancels out, and I'm only left with mole of calcium. Now let's look at one more problem. This is the toughest kind of problem of them all, but again, with the help of your mole map, I'm confident this will be manageable, and I'm confident you guys will perfect this quicker than most. So here we go. Let's start with practice problem number 3. And again, if you feel confident, go ahead and pause the video and try it. If not, you can watch me do it because you're going to have tons of practice of this in class with your lessons, homeworks. How many grams? Okay, unknown. Question mark, grams. Are there in 4.56 times 10 to the 23 atoms of potassium chloride? So he wants to know grams of potassium chloride from atoms. I wrote down what the problem gave me. I'm looking for my unknown. Now I need to start coming up with a game plan. Your game plan revolves around this mole map idea. Again, you are starting with atoms, that's this particle box, and you're converting it all the way to grams or mass. So this is going to be a 2-step conversion problem. You're going to need 2 conversion factors. You've already learned of Avogadro's number, which is 6.022 times 10 to the 23. And if you want to go and write that down on your mole map, that would be great. So what we see here, if I want to go from atoms or molecules to moles, I'm going to use this number as my conversion factor. If I want to go from molar grams, we know we use the molar mass off our periodic table. So the mole map tells me where I'm at, and it tells me where I'm going, and it tells me what stops I need to make along the way. So now we're going to go ahead and do our steps. We're going to write down what the problem gave me. Write down what you know. I know I have 4.56 times 10 to the 23 atoms of potassium chloride. Step 2, follow your unit. Atoms of potassium chloride, atoms of potassium chloride. And I see here my mole map that if I'm in particles, atoms, molecules from the unit, donuts, whatever I am, whatever I'm talking about, I can convert that to the number of moles of atom by using this number. We just make it a true statement. So I know from atoms, I can go to moles, and we know 1 mole equals 6.022 times 10 to the 23. Now I just converted from atoms to moles, but I'm not done yet because the problem wants me to go to grams. So I'm going to repeat step 2. Follow your units. Now that I'm in moles, I can see from moles I can convert to grams of the exact same compound. Now I have to understand, I have to do a little bit of what we did in the slides before. How many grams does potassium chloride weigh? Or 1 mole of potassium chloride weighs how many grams? Here's where you need to go back to your periodic table, and you see that potassium is 39.0983. We're going to call that, for the purpose of this class, to keep it nice simple, 39.10. I just simply took the number on your periodic table, went to 2 decimal places. Now, that's my grams of potassium. What about chlorine? So I see chlorine is 35.45 grams. So in order to find the molar mass of this compound, potassium chloride, I have to add these numbers together. I simply put that in my calculator, yada, 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 and you see it comes out to 74.55 grams. That number goes here. Again, it has to be a true statement. 1 mole of calcium chloride equals 74.55 grams of potassium chloride. Now I'm ready to do my math. I see my units all cancel out. Moles cancels out. I'm going to be left with this number in grams of potassium chloride. And now I just multiply across top, divide across the bottom. How do I do that in my calculator? Let me show you. So again, do it over here. I have 4.56. I need to hit my EE button to bring it up to the 23rd power. Then again, multiply across top, times it by 1, times it by 74.55. Now we're going to hit divide by 6.022 EE to the 23. And then we would again hit divide by 1. Even though it's redundant, we'll do it just for practice. And I come up with this number of 56.45. I see I have 3 sig figs here. So I will go to 3 sig figs here. My units were grams of potassium chloride, because that's on the left. And there you go. Just accomplished probably the most challenging problem you're going to see in this lesson, where it's a 2-step conversion problem. So as we wrap this up, again, I hope you understand now that a mole is just a number that represents an amount, or it could also be a mass that represents an amount. The molar mass is the mass of 1 mole of any compound or element. Avogadro's number is 6.022 times 1023. But all of these, again, is just a way to understand how much of a certain chemical or element we have. We see that it's possible to convert between all these values, and our mole map makes it very easy to go where we're going based upon what number they started with. Again, we have tons of practice. We'll be reading these different lessons in class and working on the homework. Have a great